So there is a homework due by Friday, one last homework, and most of you have submitted a lot of homework. If I cannot grade it by today, I think what I'll do is that just for attempting, I will give 4 points and return it back, which means that you don't get to, even otherwise, I'm not so good at grading, try to mark the things. So I'll just return the assignments attempting, if that's okay. If you guys really want it back, no, I want to grade it, then give it back to me. I'll try. There's too much to look at. Oh, and this is optional apparently. And I think your question was about the in-class questions, probably not more than 2 questions. Surely not more than 2 questions. Does that? Okay. We introduced the idea of Lorentz transformation. So, mostly we have been working with Lorentz transformation in 1 dimension. It's like saying rotation along 1 axis instead of, in general, we can have a 3-dimensional Lorentz transformation, which I think again, in your homework, you get a feel for it in one of the transformation problems, if I did get that problem. But the main idea we want to explore is the idea of a 4 vector. So what is a 4 vector? Take the example of x mu. So let's have a notation. So this is x mu. If we write this as, like we write the components of a vector in 3 dimensions as xi plus yj plus zk, like ijk are unit vectors. And after a while, we say that if we are always working in rectangular coordinates, ignore the ijk's, it is x, y, and z. So there is a loss of information there because the unit vectors does matter. That's a basis vector. But if we agree that we'll always work in that basis vector, then probably it's okay. But that as an approximation is there, or not approximation, that understanding is there. In those terms, we will write x mu as c times t, and x1, x2, x3. In fact, we will further put this down as c times t. It's just a vector x. This can be thought of as the fourth component of the vector or the zeroth component of the vector. Either way is okay. That's your interpretation. When I write this as a superscript, this is called a contravariant vector. This is a position, or let me come back to that. That the x subscript mu will be pretty much the same, except that either the fourth or the zeroth component changes sign. X1, x2, no, I want to keep it upstairs. Let me write this again. So you can also call this x0. It's one possibility. This one will be x0, x1, x2, x3. But then x0 is actually minus of x. But when I move the others upstairs, it doesn't cost me something, which is the same as minus CT. X1, X2, X3. And this we will often write as minus CT vector. So that is the reason why earlier, whenever we were in three-dimensional space, we didn't bother about whether it is upstairs or downstairs, because it doesn't cost a sign to go from one up to down. This is called the covariant vector.
This is different between contravariant and covariant.
Covariant is subscript.
When do we use contravariant and
Doesn't matter. You can use either one, contravariant or covariant. If we somewhere else, you will see that when you have a coordinate system, you can see it as two ways. One is intersection of surfaces. So for instance, think of spherical or cylindrical coordinates. They are intersections of circles and radial lines. Is that clear what I'm saying? Right? So those are surface. Now in two-dimensional surfaces will be curves. So either you can think of these coordinates to be formed out of these curves or the tangent to the curves. And one contravariant is got out of the surfaces, covariant is got out of the tangents. So I do this a little bit in the math method. So if you get to, if I'm teaching it, then we will see more. So at this point here, it doesn't really matter. It is just a way of writing it, and you will see why we will need it. It is important that they are different, but which one you use in this particular system, it doesn't really matter. If it is a, yeah, I think it never matters. Does it ever matter to in what context? In my limited knowledge, I think it doesn't matter, but I might be missing something. So there is a difference in the two. So yeah, it is like saying in quantum mechanics, you know, there is a bra and a cat. Like in there are this basis vectors. There is a bra basis vector and a ket basis vector. And it doesn't matter whether you work in the ket or the bra. It doesn't, as far as if it is a Hermitian system, it doesn't really matter. And to my understanding, it's a dual space, everything, there is a one-to-one correspondence between the two. So I think it doesn't really, but it's still good to give it a thought. Students, there's some special scenario where that really matters. Yeah. So, okay, good point. Okay. What is x mu? X mu. So let's define the quantity x mu. X mu. Remember, whenever an index is repeated, there is an understanding that it is sum. So whenever the index is repeated, this means mu running from 0 to 3. 0, 1, 2, 3, x mu, and that's the same as x0 plus x1 plus x2 plus x3. Change all the covariant components to contravariant components, and we know that when x0 goes to upstairs, it costs me a sign, so that's x0 plus x1 plus x2 plus x3. X0 and the contravariant component, that's just CT squared, so that's equal to minus CT squared plus this is nothing but x dotted with x. Okay. If you were to have a Lorentz frame which is moving with respect to the frame in which these coordinates are written, then if you were to measure in the new coordinate system x bar mu, where this is the Lorentz transformation, so L, let's say, how should we say that? So let's say L mu alpha times x alpha. That's that. What I'm trying to say. This is a symbolic way of writing the Lorentz transformation. Right? When you transform x to x bar, this goes away. I'm not going to explicitly do this. We have done this for one dimension before. This is exactly equal to x mu. We have done this for one dimensional case, but in general, Lorentz transformation by definition is a 4 vector remains if you want, this is the inner product of a 4 vector. We have this dot product in vector three-dimensional vector space, A dotted with B. So this is the length of this vector, if you want. Now, this is for a position coordinate. We explicitly showed that a 4 vector now, by definition, would be anything that has 4 components and remains the same. Remember again, length can change under Lorentz transformation. Time can change under Lorentz transformation. This combination does not change. So you often say this combination is the proper length or the proper time, either way, whether you define it as a negative sign or a positive sign. The combination doesn't change. So a 4 vector is any 4 components, a mu, a0, and a vector A, such that a bar This is the Lorentz transformed A is equal to mu. Change it. Okay. And that immediately gives a lot of interest in this four vectors because these quantities are invariant under Lorentz transformation. They don't change. So we would like to find everything we know in physics, we would like to have the four vector form of it. What combination of physical quantities remains the same under Lorentz transformation? That means to say that, for example, this could be momentum, right? Then you say, what is the fourth component of the momentum in such that when you have a Lorentz transformation, that remains the same. So that's our goal. And let's do a systematic way of constructing four vectors or physical quantities that are by definition four vectors. Okay, so let's go back to this. If you have x mu, so let's now call this fourth position. Or fourth displacement, maybe fourth position we already did. Maybe fourth displacement. For displacement, what we start with dx mu or x mu and construct a small change. So this will be c dt and this is vector x. dx mu then is equal to minus c square dt square plus x dotted with x.
In the first one, dx.
Oh, yes. Thank you. Let me define this to be, I'll construct a quantity called a proper time, ds squared, with a negative sign. Notice whenever it's a time, it should be negative. So that's why I brought in a negative sign. So that's just a definition if you want. And ds then is defined as the proper time. Then I can write minus ds square is equal to minus c square dt square, and take this common. I have 1 minus 1 over c square x over dt dotted with x over dt. If x represents the coordinate of a particle that is moving, then dx by dt is velocity. Same old velocity, same Newtonian velocity. We have not changed the definition of velocity. So that's equal to negative sign goes away. So I have ds is equal to c times dt times square root of 1 minus v squared over c squared, where I defined my v to be x by dt. Nothing here there. But that's gamma, right? That's 1 minus beta squared. We defined that to be 1 over gamma, right? Gamma was, by definition, gamma was 1 over 1 minus beta squared, where beta as a vector would be v over c. So ds over Yeah, so we can say that gamma is equal to C dt over ds. So often we say this is the local time, like time in the sense time in the coordinate system, but this is the proper time wherever, whoever measures that, that will be the same. So that's your proper time, that's your time. And so the idea typically is that don't work in the normal time, because all our mechanics is written in terms of time, right? Derivative with respect to time is position, sorry, velocity derivative with velocity is acceleration. Whenever we want the fourth coordinate, we want to convert all those definitions, not that we redefine, convert as much as possible in terms of S, and then read out what our four quantities are. So, and this will be a useful way to go from one to the other. Whenever we have time, go to the proper time using this relation. That's gamma, the number I have difficulty writing. That's a nice one. Okay. Any questions at this stage? Okay. So first thing we can then define is velocity. Right? For velocity. For velocity. We have x mu. So this is going to be, let's say, u of alpha. We would like 4 components of velocity. So what we will define this to be the x alpha over the s. But ds by construction, even though we set proper time, this has the units of length, right? So length over length, it is not having the dimensions of velocity. So put in a c, provide a c. Yeah, c. Thanks. Okay. That's good. So this is nothing but c times d by ds of x alpha. In our way of writing, it is ct and x. That's an explicit way of writing alpha. So what we are trying to say is take the derivative of both. So that's c squared dt over ds and c of dx over ds. Still, there is a dx over ds, convert that off again. So we have c dt over ds, comma, c, I can use a chain rule, and call this dx by dt. In fact, I can take that out. C dt over yes, c, comma, x by dt. Basically manipulations. The idea is to convert all the time references to time in terms of proper time. But now we have something more. This is nothing but gamma. So this is nothing but gamma. And this is velocity. In fact, it is good to think of this as c times gamma and v times gamma. So velocity that we usually know, it is not even the three component of a Lorentz vector. You multiply by gamma, only then you get a 3 component of a Lorentz vector. But what is invariant is this construction. This is the 0th component. So let's check if that's really true or not. So if it is invariant, you go from one frame to the other, it shouldn't change. So it's of interest to ask, what is that quantity? What is that invariant quantity associated with this? So let's calculate U alpha. So U alpha will be U0 minus of U0 plus of U capital U. And that's equal to U0 is C times gamma, so it's minus C squared gamma squared plus V squared gamma squared. Take minus C squared gamma squared common, so it's 1 minus V squared C squared. And how much is that? Equal to? What is this equal to? What is gamma squared times 1 minus V squared C squared? 1, correct? Because gamma is equal to 1 over V squared over C squared. So that's equal to minus C squared. So indeed, that's not a surprise at all. This is invariant, right? Speed of light is invariant under Lorentz transformation. So this quantity is correct. So what is the, so whenever we are thinking of velocity, and if there are 2 people measuring the velocity in 2 different frames, in 2 different labs, you're not supposed to compare your velocities as you measure in Newtonian physics. You have to measure this combination and then calculate this and compare that, which is trivial. You'll be comparing speed of light, right? So it is always will come up to be the same. So it should be the same, but velocity will not. And if you have to work, then you have to find the Lorentz transformation between them and make sure you do those transformations and then compare with each other. Is that clear motivation? Okay. This came out to be a negative sign. What does that mean? What's the relevance of that? That being a negative sign, is it a time-like vector or is it a space-like vector? So this being negative means it's a time-like. So U alpha is a time-like vector. What that means is that the magnitude of U0, will always be greater than or equal or greater than actually than U vector magnitude. That's what, and once it is, and it is also true that once you have a time-like vector, in every frame it will be a time-like vector. Time-like vector cannot be changed by Lorentz transform. There is no Lorentz transformation connecting a time-like vector and a space-like vector. Those are details I haven't emphasized on that, but somewhere else you will see. Okay, so now we have for velocity, next is for acceleration, right? So we'll keep going, like think of Newtonian physics. First we define velocity, then acceleration, then we invoke mass, and then we define force, and then we write F is equal to ma, right? So that's our goal. We would like to write F is equal to ma in Newtonian physics, or in Einstein physics. Okay. So that's for velocity. Of course, yeah. So for acceleration. Oh, before that, I should actually before going there, I should do for momentum. I think that's more nice. I think. So for momentum, is equal to that's P alpha is equal to M times U alpha. So pretty simple. So that's just multiplying the U alpha with this. So we have the clearly we have what this means. So this is M C gamma and M V. Now here is the change. So until now, whatever we have done, there is a velocity that has been defined, position, time, and velocity. Everything, we have not tried to change the definition of any of these quantities when we came in. It's just some combinations we have in mind. But this is the stage where Einstein realized that we should change the definition. So what he suggested is that the free momentum, or the let's say relativistic momentum. First, let me say Newtonian momentum. So Newtonian momentum, we will give up on this. So Newtonian momentum is P, and I'll call that, let's say that N will be equal to M times V. That's what we defined with Newtonian physics. This will be the relativistic momentum. P is equal to M times V times gamma. From this point on, whenever we write P, it means this. In any relativistic context, when we write P, it's kind of consistent that we always mean MV times gamma. There is no textbook, the textbook changes. It's always P for the MV times gamma. Immediately the question comes, what about this quantity? What is that equal to? Then we define what is relativistic energy. Relativistic energy. This is relativistic. Yeah. We cannot really say, okay, so when we say energy in Newtonian physics, there is a kinetic energy piece, there is a potential energy piece too, correct? This technically this should be kinetic energy, okay, but I'm not going to write kinetic energy. So if there is any confusion, it's going to be kinetic energy, because you will ask later on somewhere when you're thinking about this, oh, what happened to potential energy? Where does that go? So this is the generalization of the kinetic energy in here. But I'm not going to write that because it's not going to give you the kinetic energy in the limit C going to infinity. And we will see that in a few minutes. So just for your information, this is a generalization of kinetic energy. But why not? We will see it in a few minutes. So this is E. And that's not really C because that doesn't have the right units, right? So you would say it is MC squared times gamma. Right? Mass times velocity, right? That's sorry, velocity squared is. So that's your energy. If you want to explicitly write this, this would be mv over 1 minus v squared over c squared, and this mc squared over 1 minus v squared. Sometimes in some of the textbooks, they will write this, especially the popular level physics or elementary physics, when you don't want to write so many equations, you will define a mass which is m is equal to m over 1 minus v square over c square. So that's common. We will never do that. For us, mass doesn't change under Lorentz transformation. Mass remains the same in every frame. So it's called the rest mass of a particle, and that remains same everywhere. And we will see what that is exactly like c. It seems like u alpha is c square. So when I say that mass is the same, one should wonder, oh, what that means. So immediately do p alpha, and we'll move that.
Do you have a big squared?
No. Sorry. Yeah, sorry. My bad. And in fact, whatever I'm talking about the mass, when Einstein did that for the first time, he also was figuring out in his first papers, actually, he wrote, he tried to change the mass. There's nothing wrong in that. That's a matter of interpretation. I think these days you keep the mass the same unless it's a popular level physics where it is easy to write, because it's nice to write m is equal to mc squared. So that's a very popular equation. In that case, m times gamma is your m. So that's the, I think that's why they try to do that. Okay, so that, and yeah, also remember Newtonian energy. Right, here. So that's E. So this gives you the clarity that, oh, this is actually half mv squared. So this is a generalization of your kinetic energy of mv squared. Oops. Okay, so if that is really the case, one should be able to take some limit, so-called non-relativistic limit of this quantity, and get this, under what conditions is Einstein's theory or a Newtonian theory reasonably accurate to some degree of accuracy, let's say. So usually you say if things are going slow enough with respect to speed of light, then that is okay, but we should be able to see that. So let's start from this P. So let's start from P and expand. So let's say, so this is, let's say for V very much less than C, velocities, or just when V is smaller than VC, I can write a C. Right? So this is equal to m times V. Remember here 1 over 1 minus x squared. Expansion, so that's 1, what do you do this? Minus half times minus x squared. And then next term is what? That is a minus half. Then minus half minus 1, so it's minus 3 half. And then there is a 2 factorial and minus x squared, and so on. So that's the same as 1 plus x squared over 2, and then there is what, 3 over 8. So plus 3 over 8, x raised to 4, and so on. So if I want more accuracy, I keep keeping terms. Even when V is very close to C, the series is not completely correct, but if you want more accuracy, keep going. As more terms you keep, more accurate you have. So it's a controlled approximation in that sense. So that's equal to 1 plus 1 by 2 times V over C squared plus higher terms. And you indeed get that if I were to neglect this, I get MV, which is your, so this is approximately equal to, so this is Pn plus order p square over c square. This means I have neglected p square over c square terms. So I think I'm going to erase this. Okay. What about energy? How does a relativistic energy go to Newtonian energy? That's E is equal to mc square. Same idea, E square over c square. That's equal to mc square. Do the same idea, 1 plus 1 by 2 v square over c square. Keep the next term also plus 3 by 8 v raised to 4 over c raised to 4 plus terms. And you notice that mc square, the first term you get is mc square. And the second term you get is your kinetic energy, the Newtonian kinetic energy. Plus, if you want, and maybe at this level, I should write 1 plus order v square over c square, like inside of that kinetic energy term. So what is happening is in the limit, so we have what is happening is mc square plus the Newtonian kinetic energy, and that is 1 plus order v square over c square. In fact, the remarkable result is that even when something is at rest, that seems to be energy associated purely out of mass. It has a pure energy associated with mass, even when something is at rest. And that's the idea of a rest mass, just something has been created, involves energy. In fact, if you have an atom, if you have 2 protons coming in, that is binding energy, that energy can be converted into M, or the other way. You can, like the moment you say that there is energy associated with mass, you ask, can you convert this into some other form? Can it be converted into kinetic energy, or for the matter, interaction energy? And that's what's the idea of binding energy. If you have an atom, there is a binding energy associated with that, and you can release that energy. And that's the idea of a nuclear bomb, and horrific, but very conceptually very neat. It has been used, maybe not in the best way, but conceptually a big leap if you want. Any questions at this stage? Notice this is again, I have to stress that these are definitions now. These are new definitions. Right? Things have changed now. From this point on, we are not, our energy definitions have changed, momentum doesn't change, and physics in that sense changes. I said that mass is invariant. In what sense is that? Means there must be some four quantities you can construct, which is a Lorentz invariant concept. That's not very hard to see. That's already m times u alpha. If you do p alpha, what is that equal to? That's m squared times u alpha. But I know what u alpha is. Let's do this separately. So P alpha up. So this is invariant quantity, invariant in the sense that it is not going to change from one frame to other. So this is m square u alpha. So that's minus m square c square. That remains invariant. And in that, so that's we clearly says that if this is invariant, c has to not change, m has to not change. So m mass remains the same every. Right. It also says that if I were to expand left hand side, I get minus P0 and plus P dotted with P. This is the relativistic momentum. That's equal to minus m square c square. What is P0? P0 is your MC gamma. MC gamma is nothing but E over C. So I can say this is E over C, two of them, plus P dotted with P equal to minus m square c square. This is often written as energy square is equal to P square c square plus m square c raised to 4. Or even better, say energy, so generalized relativistic generalization of kinetic energy is E square c square plus m square c raised to 4. So square root. And in the case when velocity, you're at rest, this is equal to mc square. Okay, those are the new things. This was a major conclusion of Einstein's first paper in 1905. Any questions or comments at this stage? Okay, so we have position, velocity, and momentum. Let's go and calculate acceleration next. So we had, let me collect few things. There was gamma is equal to c dt over ds. That's one of the quantities. Then x mu is ct and x u alpha, we said, is c times gamma times v times gamma, and p alpha is mc square gamma over c mv gamma, and that's also e over c. So that's your summary. If you want, as of now, we have defined these quantities. Immediately you say, what about acceleration? So let's say for acceleration. Oh, I can move it. For acceleration is going to be a alpha. We start from for velocity, du alpha, and instead of the time, proper time, right? Derivative of proper time will be here for acceleration, but that doesn't have the units of acceleration. That's velocity. This is distance. So I won't multiply by c. That's just for dimensional reasons. Okay. Use chain rule, and you say this is c dt over ds, and you have du alpha over dt. That's gamma. So this is gamma times du alpha over dt. That's nothing but gamma times the time derivative of c times gamma and v times gamma. Okay. Remember, gamma has velocity in it. So gamma is 1 over 1 minus v square over c square. So when I take the derivative of gamma, I have this v at x. So we want to do that. So let's operate this out. So this is, I can write this as, let me keep this gamma outside. C times derivative of gamma with respect to the coordinate time. And now when I hit the second term, I can either hit the velocity here or the gamma. So this is equal to dv by dt times gamma plus v remains the same and hit here. So let's just, once we define that derivative, let's just smoothly goes. This is your usual Newtonian acceleration, right? We'll stick to that definition. That's your acceleration, Newtonian acceleration, and that's all that will be. There will be no relativistic acceleration. So that's your acceleration. And if we can get d gamma over dt, then we are good. We know the acceleration completely. So c times d gamma over dt times acceleration times gamma plus velocity times gamma. Notice acceleration is not even a complete term, right? There is an additional term in there if you want to really construct an invariant quantity out of the acceleration. So a lot more complicated than velocity or the position. Okay, if we want to proceed, we want to get d gamma over dt. For that, we can actually explicitly take the derivative. That's good enough, but let's use a trick. We had calculated, we had shown that u alpha was equal to minus c squared, right? So that should give us a way to calculate your the derivative of gamma with respect to time. Any questions as such? So u alpha is equal to minus c squared. U alpha is c times gamma times v times gamma. So if I were to do that, so or no, let's not replace that at this stage. We just say, let me take a derivative with respect to ds on both sides. That's equal to the right hand side is 0, right? Because c, the invariant quantity, is a constant. So that's 0. So this means that du alpha over ds times u alpha plus u alpha times du alpha over ds is equal to 0. If I multiply by the c, then this is nothing but acceleration. This is a alpha U alpha plus U alpha times A alpha. Small quiz. Show that A alpha U alpha is equal to A alpha U alpha. It doesn't matter whether you write contravariant times covariant or covariant times contravariant of the same. If it's the same vector, it really surely doesn't matter. It can be immediately shown. But in this case, you might wonder, oh, is that correct or not? So we should be able to show them. If they are the same, then this is 2 times that. So that means A alpha times U alpha is equal to 0. So while we are doing this, let's do a small point. We have already shown that U alpha is time-like. That means, visually speaking, if you have time here and Z here, it's in this, like it's in the time-like. Actually, that's not the right way to say it because that's CT and C, right? So this is, I should say U0 and U. It's in this domain, so it's a time-like vector. But then what does it mean to say that A alpha U alpha is equal to 0? Now, notice these are the tricks you use in relativistic physics. If this is an invariant quantity, if I change my frame, A alpha will become A bar alpha, and U alpha will become U bar alpha, or for that matter, covariant, contravariant components, all of them become transformed into that, right? The invariant structure remains the same. So I will have A alpha U alpha, which is 0. It is independent of which frame I am working in. Any frame I can, there are infinite number of frames which are going with uniform velocity with respect to me. I can pick any frame, calculate this, and if I calculate this quantity, the dot product of the 4 vector dotted with each other, then they will be invariant. This will be the same as this, and since this is equal to 0, that's going to be the same. So I will use the following trick. This is a time-like vector. So you have U alpha. Somewhere it is here. So in some frame, you measure this down there. There is a hyperbola that connects this. And then you ask, what happens if I change my frame? If I change my frame, this vector will show here. It could be here in different frames. It looks differently. Is that clear? So Lorentz transformation basically moves the vector on a hyperbola, right? Because U alpha is a constant. That's the equation of a hyperbola. So I pick a frame in which it is purely time-like. I pick a frame in which it is purely time-like. So if that is the case, this is equal to A bar. So let's say U bar alpha, let's say upstairs, is equal to C times, that is my C times gamma. So basically it's in the rest frame. So it's a C times gamma times V times gamma. I want this to be 0. So I want to go to the frame in which that's 0, which is that frame. In this case, it is obvious that you have to be in the rest frame. So that's equal to C comma 0. If that is the case, this is nothing but A bar 0 and U bar 0. Okay. But this is equal to 0. What does that mean about A0? This is equal to 0. This is not 0 because that's a time-like component of that in the rest frame. So at least there exists one frame out of many where the time component of acceleration, the forward acceleration, is 0. So this implies, right, this implies that A bar 0 is equal to 0. Okay. In that particular frame, calculate my A bar alpha. A bar alpha. That's equal to 0 minus 0 plus vector A squared. So this is greater than 0, at least greater than or equal to 0, which means A alpha is space-like. This argument did not care for the fact that this is acceleration and velocity. I could have taken any two vectors. If there are two vectors, one of which is time-like, is 0, then the other vector has to be spaceless. Which means that if there are two vectors that are orthogonal in a Lorentz coordinate system, if one is time-like, the other is spacelike. You cannot have a time-like being orthogonal. So orthogonality in the Lorentz frames has this feature. They are not perpendicular, by the way. 90 degrees is not a very good reference in that the geometry is not of circular geometry, it is a hyperbolic geometry. Anyway, so now we know that acceleration is space-like. So, but we said we went into all this so that we can actually calculate the gamma over d2. So we have this equal to 0. That actually will give us that derivative of gamma. Okay. Any questions at this stage? Especially this derivation. That's a sort of a few steps logic, but that's very common. Whenever you are in relativity, it's a good idea to, if possible, go to the rest frame. And is it always possible to go to the rest frame? So here is a thought problem, quiz, let's say. So let's say there is a, so the following happens. And so is the idea of a photon clear? What's a photon? Photon is a particle associated with light. It's a single particle, but its mass is 0, right? For all practical purposes, it is a single particle, but its mass is 0. So now let's say there is an electron, which we will show as this, and positron is the same as an electron except that it has a positive charge. And there is a photon. Typically, you say this is photon, it's represented by gamma. We are using gamma in another context, but that's. Now, let us consider the reaction. That is an electron floating around, right? Or positron, and an electron, they come together. at one point. And since they are the antiparticle of each other, antiparticle means they can kill each other. They can disappear, but you cannot really disappear in the sense that there has to be energy. But all that energy is taken away by the photon. Right? So energy has to show up somewhere. So you say that it shows up as a photon. So matter, antimatter comes together, it creates one photon. Right? And I say that's not possible. Is that possible? Conservation of momentum, very good, right? So the idea is that it cannot be done, and why is it not possible? Maybe explain. Why is conservation of momentum violated?
Because for the left part is 0, but for the right side is not 0.
Correct. Or the right side, whatever you do, there is no frame in it. Here, there is no rest frame, because photon is speed of light. In any frame you go, it has to be speed of light. But here there exists a frame. There is a center of mass frame. There are two masses, could be coming in opposite direction or in whatever direction it's going. There exists a frame in which they are coming in opposite direction, and there is a rest frame here. If you want, center of mass frame is at rest. But when you go there, it's not possible. Does that mean that matter antimatter cannot disappear? It can, except that now you need two photons. So you cannot give you one photon. It at least needs two or more, so that momentum can be conserved. So these kind of arguments are very useful. You don't have to do any derivations even before, just by, these are called the symmetry arguments, or what's the argument you would say? Yeah, logical arguments that you can rule out certain things happen just by that. Okay. We were talking about trying to get derivative of gamma with respect to time. Let's do that. So this is alpha. Alpha is equal to 0. And that's the same as minus A0 U0 plus vector A dotted with vector U is equal to 0. Go to your vector A is this. So it is minus of gamma C d gamma over dt times U0. U0 is C times gamma. So C times gamma. That's A0, that's U0 plus vector A. So it's A times gamma square plus B times gamma times d gamma over dt dotted with U, which is V times gamma. So vector A, U, and A naught and B naught. Write this as there's a 8. Let's simplify this, right? So this is minus C square gamma square E gamma over dt. Let me write this term first. So it is plus V square gamma square dt, and that is plus A dotted with V times gamma cube. It's equal to 0. So that's the same as minus, let me write C square gamma over dt. And what else can I do? Let me take a gamma square also out. So that's 1 minus V square over C square, and use the minus sign to move the other quantity on the left. But gamma square times 1 minus v square over c squared is 1. That's equal to 1. So I have so I can learn that d gamma over dt is equal to a dotted with v over c squared times gamma cube. Once I have that, I can substitute that in my definition of acceleration that we got there. So that's equal to gamma. So let me put the gamma raised to 4 times a dotted with v over c. That's your time component. And the next piece is a multiplied by gamma squared. And we have v. So it's a plus gamma times this. So this is gamma raised to 4 by gamma times that. Yeah. So it is gamma raised to 4 times a dotted with v over c and v over c. There is one thing that comes out very nicely in here. If you have V and A to be parallel, so V is parallel to A, which is what happens if you have an electric field, right? If you exert an electric field and if things are moving starting from rest, then velocity is parallel to the acceleration. The electric field moves the charge from rest in its own direction. So that's like electric field. Electric field. In that case, A alpha is equal to, this is A, so now everything is parallel, so it is, you can think of it as one direction. So it's gamma raised to 4, and you have A times beta, right? This is basically beta. So A times beta. So says in the direction in which things are happening, and this is A. So A now is in the same direction, so that's A can be pulled out. That is gamma squared plus gamma raised to 4 gamma squared, right? Gamma squared pulls out gamma squared and beta squared. What is 1 plus gamma squared beta squared? So that's 1 minus beta squared plus beta squared over 1 minus beta squared. So that's gamma squared. So that's gamma raised to 4, correct? So it is gamma raised to 4 A beta times A. So. But what about if A is perpendicular to beta? Final thing, no. That's what happens when you're in a magnetic field. A is perpendicular to beta. So A alpha is equal to 0, and this is equal to A times gamma squared. So the important piece is that the space part goes as gamma squared when it is perpendicular, and it goes as gamma raised to 4 if it is parallel to each other. So if you think of length contraction, length contracts, time dilates, that's a factor of gamma. But now you can ask what happens to acceleration? Does the length acceleration contract or dilate? It not only dilates, if you take this expression, it actually goes by gamma squared. In fact, in another frame, it is gamma raised to 4. One would say that we shouldn't talk about the space part at all. One should talk about the invariant quantity. What is the invariant acceleration? So immediately you say, what is A alpha? A alpha, irrespective of whether it is parallel or not. Let's immediately calculate that. Who has a class? Can I take 2-3 more minutes? Okay, you have a class? Yeah. So no one has a class. Yeah.
It's okay.
3 minutes? Okay. So square this. So A alpha is negative of gamma raised to 8 times A dotted with beta square plus this square, right? So this is vector A gamma square plus gamma 4 plus A dotted with beta, and there is the beta square. Do this quick. Actually, why calculate this at all? I just want to define proper acceleration, right? Proper acceleration is calculate A alpha. This is going to be the same in every frame, right? So why bother to calculate? I will calculate it in the rest frame, right? This is going to be the same. So calculate it in the rest frame. That's 1. That's 0. This is the only term that survives. Everything else goes away. And that's equal to, in the rest frame, this is A squared. But that's not the normal acceleration, so I have to give it the special meaning. So this is A0. This is not your 0, right? Obviously. Acceleration in the rest frame. This you give it a special name. Do you say it is alpha? Alpha is proper acceleration. But very naively, you might argue, how can you have an acceleration in the rest frame? I'm sitting in the frame, how can I accelerate? Is that possible? I'm sitting in the rest frame. How can I be accelerating? Is it necessary that if your velocity is 0, your acceleration is 0? Give an example.
Velocity is 0.
No, velocity is not 0. But in the direction of A, that's there. But anything more straightforward? Give an example of a case where velocity is 0.
The peak of a parabola.
Peak of a parabola. When you throw a ball up, right on the top, it comes to a rest. But its acceleration is still 9.8 meters per second squared. So this is at an instant possible. At an instant, because we are in a frame, we are not excluding acceleration. I'm limited now with Lorentz frames, but if I'm in one frame, I can be at rest at an instant at the most. If I'm accelerating in the very next moment, it will be I'll be in another frame. So, or the particle will be in another, or it will have some velocity. I won't be at rest permanently. So this is, so if you want to have proper acceleration permanently, you have to keep jumping from frame to frame. Right? Since it's a Lorentz frame, I can keep going from one frame to the other. So as the particle goes, I'll keep jumping from one frame to the other so that I can stay at rest. And every time I jump, I have transformed my coordinates. Unless I'm working the proper invariant quantity, then I don't have to transform. So usually what you do in relativity is that you find this quantity which is invariant, and then you keep jumping. And you go around a curve where you're always, it's called a local coordinate, local rest frame, local rest frame, and that's what. Okay, I'll stop here. Thank you for allowing me to take a few minutes, and we will do an example of a particle being drawn. Define the 4 force now. That's all thing remaining, and then do some couple of examples about just one of them, and that's will be our last class. Thank you. Yes. Thank you, Abdullah.